Good morning. So now you should have made the sample space for number 2. Number 2 had that you were tossing a die and tossing a coin. And so you could have written your sample space in one of two ways. You could have had your sample space with you toss the coin, here's heads and here's tails. And then you could have had the sample space where you say, okay, I got heads with 1, heads with 2, heads with 3, heads with 4, heads with 5, heads with 6. Or you could have said, I tossed tails first with 1, tails with 2, tails with 3, tails with 4, tails with 5, tails with 6. So again, this is your tree diagram. This is the coin with 2 outcomes. This is the die with 6 outcomes. And counting principle, 2 times 6 means you better have 12 outcomes. So I have 12 branches. Now, again, not everybody can follow the branches, so you could have also written your sample space as a list. You could have said, I got heads with tossing a 1, I got heads with tossing a 2, heads with a 3, heads with 4, heads with 5, and heads with 6. So here is the first 6 branches, or tails with 1, tails with 2, tails with 3, tails with 4, tails with 5, and tails with 6. Either sample space is fine. You don't have to do both. You just have to do one, but you have to be able to read what you wrote. Now, part B says write a set of ordered pairs that represent the event of getting tails and an even number. Call this set A. All right, so set A now is getting tails with an even number. So that would be tails with the 2, tails with the 4, and tails with the 6. Here is my set A. Then part C wants the complement. Now the complement again is the not. They want me to call this set B, but set B is also not A, either written with the symbol, or I would say not set A. So this is what B is going to be. So B is going to be everything from the overall sample space that's not in set A. So set B is going to have all the heads. Heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and then it's going to have tails with the odd. Tails 1, tails 3, and tails 5. So there now is set B. Part D, find the probability of set A and the probability of set B. Well, if I toss a coin in this hand and I roll a die in this hand, the probability that I get something from set A, which means I get tails followed by an even number, that happened 3 times out of the whole sample space, which is 12. You can reduce this to 1/4, but like I told you before, we don't have to reduce. And the probability of something from set B happening, well, set B, there were 9 items here out of the sample space of 12, and so that would be 9 out of 12, or 3/4. But again, I'm happy here and I'm happy here. There's no need to reduce. The other thing that they're not asking about, but I'm going to mention anyway, the probability of A and not A together make one whole. Look at 1/4 and 3/4 together make one whole. So if you know one of them, you can just subtract from one to get the other, and I'll show you that a little bit more on the next example. So we're on example 3. And example 3 says to draw a Venn diagram where you have rolling a 6-sided die. Well, if you roll a 6-sided die, your sample space for that, so a 6-sided die, your sample space is equal to 1, 2, 3, 4, 5, 6. Now, they want you to draw a Venn diagram where we split it into set A would be the event of rolling a number greater than 4. So let's just write out A. If I'm a number greater than 4, I'm only 5 and 6. And then we have set B, which is the complement of A. So again, B is the same as not A. And so that would be the 1, 2, 3, and 4. Now, if I were to make a Venn diagram of this would just have the overall universal set is the 6-sided die. Set A is here with 5 and 6, and set B is here with 1, 2, 3, and 4. They don't overlap at all because they were opposites of each other. They were complements. So now they want to know for B, find the probability of A, the probability of B. So the probability of getting a number greater than 4, which is what A is, so that would be the same as saying a number greater than 4. This would have been 2 out of 6. The probability of not A, which is B, so this is the same as not A. This would be 4 out of 6. Together, if you notice, for part C now, they say, what is true of the sum? Well, for part C, 2/6 plus 4/6 equals 6/6, which is 1 whole. So what is true is an event plus its complement equal 1 whole. They have to. It's 100%. It's an absolute probability. And so now they say prove that the sum of an event with the probability of its complement will always be 1. Well, if we want to prove it, if we have the probability of an event and then we have the complement, and the definition of complement is 1 minus the probability of the event, which would then be called the probability of not the event. See the not symbol? But if I add these two together, the probability of an event plus 1 minus the probability of that event, what does this equal? Well, probability of an event plus and then negative, these guys cancel, I'm only left with 1. It's going to always work. So that was exercise 3. Now exercise 4 is talking about drawing a marble from a bag. So let's get rid of all this and let's have a nice clean board for problem 4. So problem 4 says you will draw a red marble from a bag is 3 out of 17. So we have a bag of marbles. So we have a bag of marbles. Here's my bag. The probability of getting red is 3 out of 17. So that means the probability of not getting red would be 14 out of 17 because 1 minus 3/17 would be 14/17. And so then, and that was it. That's all they wanted for A. So that was part A. Part B, says the probability of rain is 20%. So therefore, the probability that it will not rain, so again, notice I'm using either the not symbol or I'm writing the word not, get used to both of them. 1 minus 20%, 80% chance that it will not rain. Now, finally, we have exercise 5 where we're rolling 2 4-sided die. So for exercise 5, we have 2 4-sided dies. Actually, that would be dice. Plural of die is dice. 2 4-sided dice. So that means on the first, I have 4 outcomes. On the second, I have 4 outcomes. And so using the counting principle, I multiply these guys together. So I'm going to multiply, and that gives me 16 outcomes in my sample space. If you do this for every problem, even problems that seem really easy, you're going to do a really, really nice job. So if I say, and I use some logic, and I say, okay, on the first die, so we're talking the first, I roll a 1. Well, now we've got to go with the second die. Now I could have rolled a 1, a 2, a 3, or a 4. Then I say to myself, well, I didn't roll a 1 on the first. I rolled a 2. On the second, I could have gotten a 1, a 2, a 3, or a 4. Then I, again, logically say, well, I didn't get a 1 or a 2. I actually rolled a 3. That means I could have gotten a 1, a 2, a 3, or a 4. And then lastly, if I did not get a 1, not get a 2, not get a 3, that means I rolled a 4, followed by probability of getting a 1, a 2, a 3, or a 4. That makes 16 branches. That is my full sample space written as a tree. You could have written it as ordered pairs. What is the probability that you don't get 2 of the same number? Well, if I look, I have 1, 1, same number once. I have 2, 2, same number twice. 3, 3, same number 3 times. 4, 4, same number 4 times. So if I want the probability of not the same number, then I can say 1 whole minus 4 out of 16. Because 4 times I got the same number. Now, just to go a little slower, back up a little bit, 1 is the same as 16 out of 16. There were 16 branches. And if 4 of them have the same number, then this means I would have 12 out of 16. My probability of not getting the same number twice would be 12 out of 16. So that was all the classwork, beginning probability. Please try to do the homework. Remember, you got to show me all 4 pages of the packet to get full credit for the day. You need classwork and you need homework. So good luck.